We are starting off with the technical sessions again for today, and the first session is R for spatial analysis. Dr. Bappa, you have a total of 90 minutes allotted for this session to cover the program as well as have participants' question addressed. I will be giving you a heads up in an hour, which is at 2:30, because your session is timed to end at 3 p.m. And then I'll again remind you at 2:50 p.m. I hope that is fine. Again, a request to participant. You can keep your camera on so that the resource person can see who they're talking to. You can interrupt the person and ask in between if you're not understanding anything. Make it more of an interaction and dialogue. Try not to make it a monologue. Over to you, Dr. Bappa.
Okay, thank you. So directly I will share. I think you have to answer. I'm
Sorry,
sharing.
you can
Yeah.
start presenting.
I'm sharing my screen.
Also, for participants, you can enlarge the screen at your end. It need not be from our end. You can make it in the view section. There is an option where uh, I think if you select side by side gallery in view, you'll have that presentation cover your full screen, so you can see it in a more enlarged manner, and it's not so small for you to look at. Because yesterday participants were pointing out that it is very small. So in view tab, you can use the side by side gallery option, and there you can have the presentation cover your screen.
Okay.
Yes, sir.
Uh, So very good afternoon to you all. So today I'll be dealing about R for spatial analysis, means how R software can be used to do some of the spatial analysis like reliability mapping, or you are having a point data, how you can make a continuous map like this. So this is in a nutshell what I will be going to cover today. So these are the topics which I will be covering, means reading and writing raster and vector data in R. Suppose you have downloaded some data from some source, as some of the research persons have already taken class on open source raster and vector data. So suppose you have downloaded all those data, so how you can import all those data, read all those data into R and do some analysis. Then correction of digital number to add surface reflectance with dark object subtraction. That is one method for atmospheric correction. If the product level is 1, that is L1 product. If you are downloading L1 product, so that has to be corrected to have the add surface reflectance. So many algorithms are there. I will be dealing with dark object subtraction, which is available in our software. Then converting the projection, because from different sources, suppose you are downloading the data, so those data sets will be having different projection systems. So you have to have a common projection system for all the layers, whatever layer you are downloading, vector layer, raster layer, in order to overlay on top of the another layer. So the operation is called as reprojection. Then cropping and masking, so you will be downloading the data, suppose for whole one scene is too large, suppose your study area is very less, so accordingly you can crop and mask the data, you can have the data for your region. Then plotting of natural and false color composite, that I will be showing in the script when I will be running the script. Then how can we import excel or csv file and make it as a shape file or vector file. Then land use land cover mapping using unsupervised as well as supervised uh, algorithms I will be showing you, and then kriging to generate map from point data, then vector to raster conversion. At the same time, we can do raster to vector conversion, that is called vectorization and rasterization. But I will be showing you rasterization that is required for our work today. Then basic raster and vector data plotting. I think some advanced plotting has been covered yesterday, but I will cover some of the plotting today also. So if we see for optical data and thermal data also, mostly optical data, the source is your sun. Sun is the source of light. Then that sunlight is coming, it will interact with the atmospheric particles. So some of the part of the sunlight will be scattered and it will be reaching on the ground surface. And direct sunlight also reaches on the ground surface. Then it will interact with different objects on the earth, like your water body, built up area, whatever is there, cropland, bare soil. So those radiation will interact with those materials on the earth surface, and it will some part of it will be reflected and going to the sensor. At the same time, some part of the uh, light energy, whatever is coming, it will be scattered and reaching to the sensor. So this part, that path radiance, that is not our interest. We are interested about the reflectance from object. So we have to somehow deduct it in order to have the characteristics objects on the surface. So that's why we are applying atmospheric correction. So whatever level 1 product you will be downloading, L1 product downloading from any source, that will be having raw DN values at sensor DN values. So that has to be converted into bottom of atmosphere reflectance. So the basic dark object subtraction, what it does, the darkest object in a scene which is having no reflectance at all, mostly it will be a water body which is having a very low reflectance. So that the darkest object, whatever reflectance is coming, we assume that that reflectance is because of path radiance, not due to the object, because it is not reflecting anything. So that assumption is there. So whatever energy is coming from the darkest object, it is only path radiance. So that reflectance of dark object we are subtracting from other objects. So that is called dark object subtraction atmospheric correction. So then I will be covering land use, land cover. You can go through all this. I will not go into detail of this because I have provided the slides. It will be shared with you. You can read all these things, how it can be done. So today we'll be using Landsat 8 and 9 data also can be used. And nowadays, these level 2 products are available, means already atmospherically corrected data are available from Earth Explorer or Sentinel Hub, Sci-Hub, Copernicus Sci-Hub platform. So also Google Earth Engine can be used to download the L2 products of Landsat 8, 9, Sentinel 1 and 2. But I will be showing you how to do the atmospheric correction if you are having level 1 product. Then pre-processing, as I have told you, geometric correction, already those products are geometrically corrected. That means they are having proper latitude, longitude information with it. Then radiometric correction, that is atmospheric correction, we will be doing it. Resampling means having the rasters or rasters mostly at the same pixel resolution. So suppose you are downloading Sentinel 1 or Sentinel 2, those are having resolutions of 10, 20 and 60 meter. The Sentinel 2, 10, 20 and 60 meter. Sentinel 1 is having 10-meter resolution, whereas Landsat 8 is having 30-meter resolution. Suppose you want to use both of these for your land use, land cover classification. So you have to do resampling. You have to make the pixel size same and you have to make the projection same in order to overlay all this raster data. Then we can have supervised and unsupervised classification. Also hybrid classifications are there which combines both supervised and unsupervised classification. Then we have to do post classification accuracy assessment using some metrics like matrices like producer accuracy, user accuracy, kappa, overall accuracy. Okay, so pre-processing, I will be showing you directly into the R Studio. And if we see the flow of pre-processing, this is the first one. You will be getting DN raw DN value or at sensor DN value, that is digital number, that has to be converted into at sensor radiance with some specific constant value, which has been provided in metadata. So those scaling factor you have to apply. That will be dn value will be converted into radians. Then that radiance can be converted into top of the atmosphere reflectance using some of the parameters like earth sun's distance, solar zenith angle, extra atmospheric radiance. All these will be provided into the metadata. When you will be downloading the data, some metadata file will be downloaded with that. So from that file you can get all those information. Then we have to do the atmospheric correction, which requires knowledge of atmospheric condition at the time of image acquisition, whether it is having a haze, some kind of thing, haze or whatever things, cloud cover is there. So those part you have to remove. So that will give you bottom of atmosphere or surface reflectance. Then add when you are ready with the data, when the pre-processing is done, then it is ready for image classifications. So for image classifications, we are assigning the pixels in the image to categories or classes of interest like crop area, cropland, like agriculture, forest, built-up areas, water body, bare soil, etc. And different classifications can be used like supervised, unsupervised, and hybrid. The supervised classification where the who is the operator is the master, means we are having upper hand, we can control the classification system in case of supervised. and we have to give some training set or ground truth. And in unsupervised classification, the system is the master. So the computer will generate some of the classes, and we are not having any control over that, um, except the number of classes. We can specify the number of classes, but we don't have any control after that. So some of the advantages, disadvantages I have given, and examples are maximum distance to mean, parallelepiped, maximum likelihood classification, and all the machine learning models like random forest, artificial neural network. Those are coming under supervised classification system. And in unsupervised classification system, we are having ISO data, k-means classification system. Okay, so I'll be giving you one example of IARI. This is Indian Agricultural Research Institute located in New Delhi. So there is a farm area of that institute, and we have collected various ground truths. So these are the ground truth data using GPS. So we have done the ground survey, and this will act as a training data for you. And then we have tried to classify it using, I think, random forest, and then we have tried to see the accuracy and kappa, though the accuracy and kappa was less. But this is using only Landsat 8 data. So that I will be showing you in during hands-on. Then I will be talking about giving hands-on on spatial interpolation. As I have told you, you might be collecting data through GPS. So suppose some surveying you are doing, soil survey. So you will be having GPS data as well as soil samples, and you will be doing some analysis of those soil samples like organic carbon in pK, whatever parameter you are interested. You can do all those analysis in the laboratory. Then you are having only point data. So you want to generate from point data to a map. So that process is known as spatial interpolation. So there are different types of interpolation technique like global interpolation, local interpolation. I have given examples like kriging, inverse distance weighted method. In global, you are having spline, linear regression, thin surface analysis. Then some of the deterministic method, and another classification is deterministic and stochastic. In deterministic, we are not measuring the errors associated with the prediction. So the examples are spline, teen, IDW, nearest neighbors. And in stochastic, the error is also measured at the with the estimation of the map of any property with its error will come. So these methods are includes kriging and pro-kriging. So some of the techniques I have given all the details like Thessian polygon, inverse distance weighted interpolation. So Thessian polygon I will not be dealing, but inverse distance weighted interpolation you might be uh, encountering in many of the literature. So I'm dealing here. The here what we do actually, suppose these are the 3 points, this point, and this point. These are the closest 3 point where we are having known values like 100, 200, and 160. And we this yellow dot, we want to measure the value at this yellow dot, and the distance is there, that is 4, 3, and 2. These are the distance from this brown points. So we already know the distance, that is d, we know, and z value we know. We have to estimate this one, z value. So this is the formula. Here you can see the distance is downside, that is inversely proportional. So here we assume, what we assume, that the values, the points which are more close to unknown location are more alike as compared to the points which are far away. So that distance is used to calculate the weight, okay, in an inverse way. So this is the formula, and I have also shown how to calculate this unknown value. So you have to calculate 1 by distance square, so 1 by 4 square, then 1 by 3 square, 1 by 2 square. You can have the total value. Then the values should be multiplied by these weights. Values should be multiplied those weights. This will give you, and summation you can have, and you have to divide this by this value. So this total divided by this sum. So that will give you 176. So this is the unknown value, that is 176. So this is programmatically done using R software or any GIS software. You can use ArcGIS also, QGIS also, IDW is available. So those are done programmatically. Then the next, the stochastic method. Yeah, IW was deterministic method. Then the stochastic method is kriging. which assumes spatial variation of a continuous attribute is often too irregular to be modeled by a simple function, which we have seen earlier. This one, this function is very, very simple. So, so in reality, the things are not that much simple. So we have these equations where we have a random spatially correlated component and a residual non-spatially correlated term or noise. This is error and a random spatially correlated component with the deterministic function that describes the structural relationship of Z at a particular location, that is X. So this is the basic equation for Kriging. So there are different steps for doing the kriging. Then first you have to check whether there is a trend is there, spatial trend. Then checking up for stationarity and isotropy. We have to check. Then computing the empirical variogram that I will be showing. Then fitting and selecting a theoretical variogram model to empirical variogram. Computing the weight. Then predicting the values at location of interest. Then validation of the map which will be generating and plotting the kriging surfaces. So uh, as you are coming across this variogram, so what is that variogram? So this variogram is relationship of lag distance with semi-variance. Okay, the semi-variance, it is like the variance, you might be knowing standard deviation on variance, but one half of that. That's why we are calling it as semi-variance. So 1 by 2 nh and I is equal to 1 to nh zi minus zi plus h square. Means if you are having observations at ith position and you are having observations at zi plus h location, that can be used to calculate the semi-variance using this formula. Okay, and typically the semi-variance look like this. So you are having a lag distance here and semi-variance value here, and your points will be like this, observe point, and we have to fit a empirical semi-variogram, and there are three parameters are there. You have one parameter is seal, one is range, another one is nugget. Suppose you are taking a observations from a same location twice, thrice, in number of times. Ideally, the value of that parameter should be same because we are taking the observations from a same location, but it rarely happens. If you measure a sample in number of times, different times, you will be having a different results. That may be due to your sampling error, measurement error. So these are the errors. So that is causing variability when there is zero distance. So that part is known as nugget, and the distance where the parameter value become independent of the if you are increasing the distance, the parameter is not changing. So that distance is known as range, and the value at which it becomes space independent, we call it as fill. So these are the three parameters which we have to estimate when we are fitting the Kriging model. So there are different type of kriging model like ordinary kriging, simple kriging, universal kriging, residual kriging, indicator kriging, co-kriging. So I have given all the details. So I'm not going into these things. So I'll directly go into my R Studio. So I have already provided the script and the data set in the folder. You can download it and you can go go along with me. Okay. So is it visible clearly? Anyone can respond. The codes.
Yes, yes,
Uh,
it's very
it's visible,
visible
no?
and clear.
Okay.
Yeah.
Oh, okay. So as I have told you yesterday that you have to install the packages. So for that you have to use the function that is install.packages. So today I will be using one package that is called RS Toolbox, Terra, SF, Simple Feature, and Stars. These are the package which I'll be using, and our color ramps that is for coloring the maps. So these packages I will be using, and R is having a very good documentation. Suppose you want to know about this package, so in Google just you can type it RS Toolbox R package. So you can open this one, CRAN, as I have told you. Uh, this is whole this comprehensive R archive network. You can open it, and then you can see reference manual is there that you can open reference manual. And what are the function in is there, whatever functions are there in that package, it will be saying index. In the index you can have, and the details of the functions, this kind of functions, then what are the arguments you have to use, the details, the output, what will be the output with example. You can find in the internet. Also some descriptions will be there, what it does, what the function does. So this way you can have the details about all these packages. So just you can run this by putting your cursor here and putting the run here. Okay, so I'm not running all this because already I'm having all this package installed in my system. Okay, then once you have installed those packages, no need to install it again and again, but you have to call those libraries every time. So from line number 6, you can see line number 6 you have to run every time. So I'm running. So you can see those packages are getting attached to my current session. And I have provided one data also, that Landsat 8 data I have provided in the folder, because this is around 1 GB data. So if I download now, it will take some time. So already I have downloaded and provided the data in the folder. Okay, and as I was telling you that when you are downloading the data, there will be one metadata file that is known as MTL file, metadata file in TXT format, text format. So you can open it using Notepad++, and you can have the details of the data. Yeah, Landsat metadata file, you can see product content, what are the things. Then Landsat product ID is there. For processing level, as I was telling you, this is L1 product I have downloaded, but you can have L2 product also. So to show the atmospheric correction part, I have downloaded the L1 product. Then some of the file names, whatever file is provided in that folder, file name is written. Then that file type is provided. This is UINT16. INT is integer. I told you yesterday that integer is a data type that doesn't have any decimal places. So INT. But what U signifies here? U is unsigned, means they will not have any negative value. All the values will be having positive sign. So unsigned, we are telling. If it is having positive and negative both the values, then that will be signed integer or signed float, something like that. And it's a 16-bit. This one is 16-bit information. So those are the details you can have. The product is Landsat 8, only TIRS, that is the sensor ID, sensor name. You can have the path, row number, path number, row number. Then the Nadir image already, most of the remote sensing images are collected at Nadir position, that is directly downward looking from the sensor, directly downward. It will be capturing, and the date acquired, when the image was acquired, that thing you can have. Since sensor time, those details you can have. Then sun azimuth, as I was telling you, these are required: sun azimuth, sun elevation, then sun earth distance, to convert the DN to at sensor radiance value. So these coefficients are required. Then you can see projection also there, map projection. It is UTM map projection. Datum is there, WGS 1984. Zone, UTM zone, because UTM is having multiple zone, around 60 zones are there. So this area is falling UTM zone 43. So this way you can have details of the product. Many things are there. You can go, then you can have the maximum value or minimum value of the radiance, then quantized values. These constants are important. K1 constant for band 10, K2 constant for band 10. If you are doing thermal image processing, then these constants are required. K1 and K2 constant for band 10 and band 11. These are thermal bands. So for thermal image correction, these band informations are required. But no need to worry here, because R will do it for you. Okay. So that file, metadata file, we are reading. So we are giving the directory name and the file name within inverted comma, and you have to use double backward slash, as I have told you, to provide the directory. So it will read your MTL file, and your MTL file can be seen here in the environment. Then one function is there. This function is coming from RS toolbox. Whatever atmospheric correction I will be doing, it is from RS toolbox package. So you have to use read meta, means it will read the metadata file. So it will read the metadata file. Sorry, so the directory I think I have to give has to change. So double backward slash you have to give, and then you can run. Yeah, now it is running. So this, if error is coming, then it will not run. You have to check if errors are coming or not. So then you can go ahead with that if errors are not there. Then we have to stack the metadata or stack the files using stack meta function. So this metadata file, whatever we have created, this meta file, whatever we have created, we can use this function to stack them, stack metadata. And as I've told you, you can, if you want to know about any function, just put a question mark and then stack the function name, and you can run it. The help will appear downside. What it is doing, from which package it is coming, and description, then arguments, and example also will be there for you. Then the important function, that is rad core function. So this will do your atmospheric correction. So this will convert your DN value to at surface reflectance using DOS algorithm. So if we see what are the algorithms available in this, you see method is APREF, that is apparent reflectance, then RAD, that is radiance, SDOS, then DOS, dark object subtraction, and COS-TZ. So these 5 methods are available for atmospheric correction. You can have the details of those methods and in which paper it has been published, from which paper it has been taken, that is also given. Okay, some details you can have. So I am using this COS-TZ function, COS-TZ method, as it is the latest. It has been published by Chavez et al. In 1996. This is the latest method. So I am using the latest method. So you have to provide the metadata and you have to provide the stack meta, means the stack of the raster data. So whatever bands are there, those stack, this is the stack and metadata, and then method you have to specify, then just you can run it. And I have assigned it in the object name lstat, that is lsat underscore surface reflectance, S reflectance. So just you can run it. It will take some time because I am processing the whole image. You can see this is the whole image in box form. So it will take some time because around 1 GB data it is processing. So depending on your computation, this speed will depend. If you are having a high-end computer, then it will be very fast. So it is doing again something is doing. And when the code is running, you can see here some red button will appear, and this arrow is not appearing. Here it is blinking. So that means the code is running. You have to wait until this red button disappears, or here one that arrow is coming. Yeah, now it is over. You can see that red button disappears. At the same time, we are having one arrow here. So that signifies that process is over. So there is one function called name. So names within bracket, if you are providing this object within bracket, so that will give you the name within that object, whatever is there. So it is giving you B1 SRE, SRE surface reflectance, and band 1, band 2, band 3, this way. But for B10 and B11, you can see this is written as BT, that is brightness temperature. So for B1, B10 and B11, those are thermal bands. And so those products are called brightness temperature. Otherwise, those other bands are surface reflectance. Okay. So you can know about the projection system, whatever projection system is there in this raster using CRS command, CRS function. This CRS coordinate reference system, that is the full form. And in short, this is CRS. So CRS, then you have to provide the object name, then comma, proj is projection. Projection is equal to true. So if you are running this, it will give you the projection name in this format. Downside in console, you can see proj is equal to UTM, that is projection is UTM, zone is 43, datum is WGS 84, and unit will be in meters. So that thing we can very easily see from our metadata file also, and from within R also we can see all these things, the projection of the data. Then if we plot it, suppose no other way to see the data in R, so the only thing you have to plot it. Suppose we want to plot the first band. So with double third bracket, you have to provide, and you can have the plot. Yeah, here. This is the whole data. You can see, we all know that reflectance varies between 0 to 1. So it is now having 0 to 1 reflectance value, and the whole scene has been plotted. But if we process all the whole scene, that every step will take some time. Our study area is something else, some smaller area. So for that, I have also provided one save file that is that can overlay over this study area. So that save file also I have provided. So you can directly provide the directory name here. We'll read the save file. Save file will having an extension of SHP. SHP. So you can run this one. This is vect. Vect the function is coming from Terra package. So this is used for reading the save files. So you can read it, and you can have the coordinate system by using coordinate CRS. Again, it is coming from Terra package. So you see, projection is latitude longitude, that is geographic coordinate system. Data is WGS 1984, and for remote sensing data, it was UTM zone 43. So these two are different. So we cannot plot, we cannot have the save file on top of the remote sensing image, but we can see the image. We can see the vector file using the plot function, and you have to provide the object name within the bracket or parenthesis. So this is the study area save file plot. Then we have to reproject it, as I have told you in during my presentation also. So these two are having different projection systems. So we have to reproject it, and for reprojecting, the function is project and then object, first object which you want to uh, convert, whose projection you want to convert, and then you can use the coordinate reference system of the satellite image. So this is the coordinate reference system of the satellite image. We are specifying CRS LSTAT as we have called it here. Also, we are using the same thing, and you can run it, and we are saving it into a object named as IRI underscore SHP underscore UTM, as it is having a projection of UTM. So that I will be running it, and again you can plot the surface reflectance value, the remote sensing image, and on top of it you can plot this using this add equal to true argument. If I use add equal to true, it will be plotted on top of it. You see very small black dot appears here because the study area is very small. Okay, so the next step is we have to crop and mask it. We want the remote sensing data of this area only, not all others. So the first function is crop. So within crop, the arguments are you have to give the remote sensing image, that is any raster image. Raster image you have to give, and then you have to give the save file. And we have assigned the name as assigned it as a variable lstat underscore s ref is surface reflectance dot crop. I'm running it. You can see now this is the data. So what cropping does, actually cropping will generate a regular shape, means whatever that vector data was there, this extent will be used, largest possible extent will be used, and the raster data will be cut according to that shape. Mostly rectangle shape will be coming. Okay, but we don't want all this outside area, outside of our vector file. Again, we don't want. So that function is known as mask. So again, you have to use this crop image, and you have to provide the shape file, and the function is mask. And we are assigning it as lstat surface reflectance dot mask. Now you can plot it. You see the outside area, we could able to delete the outside areas. So now the data is ready for further analysis. So now you can have the names also. Same name will be there. You can see the names also here, band names. Then one property is there that is called true color composite. Whatever we are observing, the leaf or vegetation, they are having green color. So we are representing those as green color into the screen also. And whatever the surface object, whatever color it is having, we are representing the same color in the computer, that is known as true color composite or natural color composite. And for natural, if you see the band names of Landsat 8, the fourth band is your red band, then the third band is green band, and the second band is blue band. So we are assigning red to red, green to green, blue to blue, and we are using a stretching function that is called stretching. Means suppose your scene, this scene is having a reflectance value varying between 0 to 255. Suppose 8-bit system you are having, so that values will be having 0 to 255. But the reflectance are mostly concentrated in between, suppose 100 to 150. So the space in the computer we are losing, starting from your 0 to 100, and again 150 to 255. There is no information, but we are losing the screen space. So we can go for histogram stretching. If you type this in Google, histogram in image processing, so some images. This is the image. This thing you can see. Suppose original image is varying between 0 to 255, but your objects are having reflectance between 84 to 153. So what it will do? It will stretch it based on the histogram distribution. You see, here the distribution is much more as compared to here. The objects are much more here as compared to this region. So for this area, the screen space will be provided more as compared to this part, the smaller part. So this is known as histogram stretching. So you can do it directly, and we can see the plot of two color composite. So suppose here some these are the actually agricultural plots. You can see those are appearing as green, and the building areas will be appearing in gray or white is in color. Also bare soil will appear in white in color. Okay, but in remote sensing we mostly use false color composite. Here what we do, actually the NIR band that is not visible to our eyes, but that contains most of the information as far as vegetation is concerned. In NIR band the reflectance is maximum. So we want to assign the NIR band to red band, and then the red band is assigned to green, and the blue band is assigned to the green band is assigned to blue color. because the NIR is not visible to our human eye. So we want to assign some color which is visible to our human eye. And at the same time, the red color, in red, the tonal variation is much more. Our eye is much more sensitive to tonal variation in the red color as compared to other colors. So small variations in the vegetation conditions can be captured by red as compared to green or as compared to blue. So you may ask a question, means why we cannot assign the NIR band to green or to blue? Because the tonal variation in gray, our eye is that is green, is not that much sensitive, or blue, our eye is not sensitive, but our eyes are more sensitive to variations in red color. That's why the NIR band is assigned with red color. So if we go ahead with this, you can see. So whatever vegetation is there, the vegetation will appear in red in color. And you see in true color composite, this appears as a dark, as a light green, and in also we can have within this dark area also dark red appearance is there. Some tonal variations we can see. This may be a forest area, deep red color, and these are agricultural area that we can very well make up, and other these are the bare soils or built up areas. So this is a common convention that is used in remote sensing community to go for a false color composite where NIR is assigned as red, then red is assigned as green, and green is assigned as blue. And then you might be having some of the data set, means you might have surveyed this region for your region also, means you have gone into the field and you have collected the GPS data and land class, whatever land cover classes are there, you have to collect those data. So for LULC classification, so this is the data set, how it looks. I want to show you this way: latitude, longitude, and class. So bare, built up, then crop, then some plantations are there, again some crops are there. So around 261 samples we have collected. So that I will be reading here. So you have to change the directory. So this way you can read the data. We can see the head of the data, as I have told you, and then class of the data. This is the data frame. I told you that whatever data are reads, that will come as a data frame, where you can see this is a character variable. Class is a character variable, but this latitude, longitude, these are numeric variable. We can hold both a number of kind of data types within data frame. We can see the structure of the data. Here we can have the details. It's a data frame with 261 observations of 3 variables, where latitude is a numeric variable, longitude is a numeric variable, class is a char character variable. Okay. Then this is a data frame, but we have to convert it into a vector format. To convert it into a vector format, you can use the vect function. As we are reading the data with vect format, we can convert the CSV file to vector format or shape file format using the same function, that is vect. You have to provide the geom in this way. This will remain same, means whatever name you have given for longitude within the Excel sheet or CSV sheet, and latitude you have to provide that within inverted comma, and then you have to provide the CRS, coordinate reference system, that is always will be in latitude, longitude, geographic coordinate system. Whatever data we are collecting through GPS, that is having a geographic coordinate system in latitude, longitude, and data means WGS 84. So this way you can create a shape file from a CSV file. Then if you run the class, it has changed. You can see it has changed into spat vector, means spatial vector file, and the package is Terra, using Terra package. You can have the structure also. It is saying S4 class spat vector package Terra. Then we can have the CRS also. CRS of already we have assigned, and we can see that the assigned CRS it is showing. Projection is latitude, longitude, data is WGS 1984. Also, we can write this vector file. So for that, the function is write vector. Then you have to provide the object name, then the file name within inverted comma. File name should be provided within inverted comma, and you can use overwrite equal to true. Suppose this file is already existing in your folder, so it will show some error. So what we are telling exclusively, we are telling that you overwrite whatever is there existing file with this, the current one. So I'm not writing this one. You can also plot this. Okay, no, it will not come. Because why it is not coming? Because the projection systems are different. Your remote sensing image was having a projection of UTM, but here the projection system is latitude longitude. So that's why we are using plot GCPS add equal to true. It is not working. So the next step is you have to reproject it. Again, the project function for raster and vector, this project function will work. Then you have to provide the object which you want to change and the coordinate reference system. Just you run it, and now you can plot it. You see, now it is showing from where we have collected the data from the study area. Then this data can be directly used for unsupervised classification. And here I am using k-means clustering. This unsuper class is coming from RS toolbox package. Just you can provide question mark and unsuper and hit enter. You can have the help. This unsupervised unsuper class coming from RS toolbox package. So unsupervised classification clustering of spat raster data using k-means clustering. So you have to provide a image spat raster in the spat raster format, that is spatial raster format. Then in samples, default value we have used here, that is default value, and you can have the number of classes. You can assign the number of classes. Whatever number of classes you want, you can assign those number of classes. And then some end start. So we are using default value. N iter, the number of iterations, we are also using default value again. Normalization, we are using true. Normalization means suppose your data are coming from different sources. So they will be having different scales. Suppose some data is varying between 0 to 1, your reflectance value is varying between 0 to 1. Thermal data, LST data will be varying if it is in Kelvin, so maybe 237 to 350, something like that, 310, 320 degree, 320 Kelvin. So these scales are different. So what computer thinks, when the values are larger, those are more important. It assumes like that. So what we are doing, we are doing normalization. So it will normalize the image, and all the layers, raster layers, will be having a same range between 0 to 1, whatever may be. So those things, it will be converting into same scale. Then cluster map, we want the cluster map, so we have to give it as true, keep it as true, and different algorithms are there. So I am using this default algorithm, but you can have other algorithm also. 3 algorithms are available, so I am using this one, Artigan 1 algorithm. So just you have to change this one according to your image. This image name you have to change, and number of class you can change. Otherwise, you can use this whole code and you can run it. So it is very fast. You can see as our area is very small, it is running very fast. And we can have the plot of our classified image. So as we have given 9 classes, so it is showing 9 different colors in the image. But we don't know what is what. 9th class is what, 1 class is what, 2, second class is what. So physically you have to verify, go to the field, and you have to assign those classes. 9 means what, and 2 means what, 3 means what. So physically you have to verify all those. Then the next technique is maximum likelihood classification. That is a supervised classification technique. Means you have to give training data here. So you can check the details about this supervised classification. Again, you have to provide the image data in spat raster format. So spat raster format is coming from Terra. You have to use Terra with RS toolbox. Then train data you have to provide. You see, train data should be SF or SP, spatial vector data containing the training location. So you have to use SF or SP package. So I'll be using SF package, as I have told you, this SF package I'll be using. So this spat vector format, this unsupervised, the supervised classification, the function, it will not accept if you provide this spat vector format. So we have to convert it into SF object. Then you have to provide a response call, means which one is the response variable in your data. For our case, it was class, bear, crop, agriculture, that column. So that you have to specify within inverted comma. Then in samples by default it is 30, I think. No, in sample you can increase also. So I'm keeping it, but for your research purpose, if you are using, you can give more in sample. Then the model is MLC, that is maximum likelihood classifier. Then the mode is classification. As our there are two kinds of statistical technique. One is classification, another one is regression. So in classification, the dependent variable or response variable will be your categorical variable. And in regression, your dependent variable will be a numeric one. So that is the only difference. And in our case, that response variable in was character or categorical. That's why we are using classification. We can also use it for regression. Then train partition means we want to use 70% of the data for training and 30% of the data we are keeping aside for validation. Then we are doing 5-fold cross validation, and verbose equal to true means it will give some thing when it will be running, some instruction, something, whatever output is there, it will be giving some instruction. Okay, so many things are there, you can read the details, but the minimum what is required to run the function I have provided here. And you have to use set.seed within bracket any number to have a reproducible results, because if you run it a number of times, the results will be different. To have a reproducible result, you have to use set.seed. So our this GCP underscore SHP underscore UTM was having spat vector format. If you see, this is a spat vector format that it doesn't accept. So we have to convert it from to SF object. So from SF package, we are calling this function st and as SF, st as SF, and within bracket you have to provide the object name. Now we can run it directly. So you see, verbose means it will show whatever it is doing. Also some model summary it is showing. So around 180 samples was used for your training, and 10 predictors were there, predictor variables were there, 4 classes were there, bear, build, crop, and plantation. You have to keep that in mind, that don't use something like space, build space up, agriculture, something like that. It should be continuous. So build up, you have to write it in continuous. Otherwise, some error may come. Don't use space or the dash. You can use underscore, but no other thing. Okay, better to use directly, means built up, running format. So we have used 5-fold cross validation here, and we can see the accuracy and kappa, the training accuracy, training kappa. We can see. Then it will generate confusion matrix also for you. You can see the confusion matrix. So this way, uh, uh, these columns are representing your trained data, and predicts these rows are representing your predicted map. So predicted predictions. So we have to have this diagonal element as much as high as possible, because this diagonal element indicates the correct classifications, and non-diagonal elements are indicates that misclassification. So we can have a accuracy that is this. If you have to sum all these diagonal elements, so 1 plus 5 plus 11 plus 3 divided by the total number of elements used for classification, that will give you accuracy. We can have confidence interval for this accuracy. What is the confidence interval? Then p-value also you can have, then kappa you can have. This is only calculated when your data is binomial, means yes and no, only two classes, 0 and 1, two classes are there, then only this parameter test p-value, that name or something, test p-value will be calculated. But we are having more than two classes, so it will come as na. And other parameters also it will calculate, like sensitivity, specificity. You can read all these in the internet. These are very well documented in literature. So read the details about all these parameters. Okay, and now we can have the image. Uh, you can see whatever you are providing here means bear you are providing as the first. So that number one class represents bear. The number two class is represented by built. Number three is your cropland, and number four is plantation. Okay. So you see this I know as I am having an idea about this study area. This is a road, and on the road side we are having trees. So you see plantation. So trees are represented as plantation. So here also some forest area is there, some trees are there. So this is represented here, and these all are cropland or bare soils. This blue color and dark blue, this cyan maybe, I don't know, green color, and this blue color, deep blue color. These are bare soils or agricultural cropland. So if you want to write this, you can write it using this function, write raster, and then img, this is the object, img underscore mlc dollar map, that will subset, because this object contains many things. You can see this contains the map, this contains the accuracy informations, validation accuracy information, but we are interested about the map here to write it as a raster. So directly you can run it. You see the error is coming. Write raster, as we have kept overwrite is equal to false. Write raster file exists. Already the file is there. So you have to do t, you have to put t there, t or true, whatever. So now it has written. So within the directory, working directory, that is, you can write get wd, you can have the working directory, and within the working directory, this has been written mlc.tip, and this can be opened in any software like your QGIS, ArcGIS, and you can have your symbology. Now I'll be showing another classification scheme, that is random forest. Okay, just you have to change the model here, other things remain same, and you can use around 237 models available in the carrot package. Any model you can use. Okay, so you can have the list here like this, carrot available models. If you type in the Google, you will have carrot available models. So these are the list of the models. What type of analysis can be done, like classification on regression? Some models are doing are only for classification, some are for regression, and some are for both classification and regression. And which parameter, tuning parameter, hyperparameter, which are optimized using this carrot package, that is also written. You see 238 models are available. Okay, so I can share this, maybe you can copy, just you can write carrot available model, and in Google you can get all the model list. So all the advanced model you can use, like random forest, support vector machine. So I'm running one. You can see the accuracy, you can see as compared to your MLC, the validation accuracy, you see validation summary, it has increased significantly. Kappa and accuracy both has increased significantly. Earlier it was around your kappa was 0.53 and accuracy was 0.68, and when we have used random forest, the accuracy has significantly improved, also the kappa, you can see that. And we can have the map of that, map of the classified image, and we can write that, and we can have a map in any software. The next part I will be dealing how to use R as a GIS package, means how to use R for spatial interpolation. So for that we have to use this package, AutoMap package, and OpenXLSX. That's not required here, because if you want to read Excel data, you can use this OpenXLSX. So I am having.
Dr. Das,
Hmm,
so sorry to interrupt. Just wanted to give you a reminder that you have 30 minutes left
yeah,
to complete the session and address participants' queries.
yeah. By 2:50 I'll be completing.
Sure, sir.
Okay. So you have to install these packages, AutoMap and OpenXLSX. So I have already installed it. Just I'm calling it, attaching it to my session. And suppose I will show you if you are having Excel data, how to run. Suppose this one, soil moisture data. Yeah. So this data, suppose I want to run it, load it. How to load it? So what you can do, you can click Shift button and then right click on your mouse. So here you can have copy as path. This one, copy as path. So directly you can copy it and put it here. Okay. So it will generate inverted comma also with it. I'm deleting one, and then the package is function is XLSX. Okay, and then again double backward slash you have to give, and you have to assign. You can give the seat name, because in CSV it can store only one seat, but for Excel we can have multiple seats. So we can give the seat name also here. So this way we can read the Excel data. Now you can see latitude, longitude, and soil moisture. But if you see the structure of the data, again, STR, that is data frame. Data frame, it contains 250 observations of three variables, latitude, longitude, and soil moisture. So it has to be converted into WAV file. So, and this AutoMap package is actually linked to SF package, not with Terra package. So we have to use this one, st as ff, this function. Then we have to provide the data frame name, then coords. Coords means coordinate. Again, same thing, that where in Terra it was geom, and in case of SF, this is coords. C within inverted comma longitude and latitude, and coord CRS. Other things all remain same. So this data frame is converted into spatial data frame. Okay, now we can plot it. Okay, some of the data is outside my study area, so that I have to check. Okay, uh, and delete those. This happens due to data entry problem. Okay, so for now I will be using my earlier data only, whatever is there, because this is having two points is problematic in that. So I'll be using this data only. Same thing, you can have a plot. You can see this will give you variability uh, in the soil moisture. We have collected the soil moisture with GPS locations. So you can see with the color, you can see the variability in the soil moisture. Okay, and this is having a CRS of lat long, that is geographic coordinate system. So it has to be reprojected into a projected coordinate system. For any kind of interpolation, this is a very important step. Means you have to convert it into some projected coordinate system. So here you have to use ST transform. This is coming from again SF package. ST transform, the data you have to give, and then CRS. You have to specify the CRS. This way you can generate it. Then you can generate the variogram. And for variogram, the function is autofit variogram coming from AutoMap package. And the arguments are you have to provide the y variable tilde 1. By default, we are writing 1 here. And the data name. The data name is df underscore utm. And we are assigning it into a variable that is called variogram. Just run it. And we can plot also. You can see the lag distance and semi-variance, as I have told you during my PPT presentations. So these are the sample observed points, and we are fitting the empirical variogram. And the model is STE, nugget is 49, seal is 70, range is 503, and it is giving some parameter that is kappa is 2. So these three parameters we want to estimate using this autofit variogram function. Then another thing you have to read the boundary file. You need the boundary file. So again, I have to copy the path and provide it here. and I am using stread. Stread is coming from SF package to read the shape file. Okay, so this layer is pusa boundary, and it's a E3 shape file. It is saying that it's a E3 shape file, the polygon file. Okay, boundary file will be polygon only. Then we can have the projection of that. That is lat long geographic coordinate system. We can plot that boundary also. If you want to plot the first one, you can use this way. This way you can subset it, as I have told you yesterday, that for subsetting you have to use a third bracket, and within that you can provide the number. If you want to first subset the first one, if you want to subset the second one, you can provide the two number. Okay, for raster, you have to use double third bracket for subsetting. Okay, so we have to convert it again into the UTM. So we are converting it using ST transform function. Again, the data you have to provide and CRS you have to provide. The CRS is written like that. Also, you can use EPSG code. You can type in Google that EPSG code for UTM zone, sorry, zone 43. Okay, this UTM zone will have a prefix of 32, and this 43, you see 43 is the zone number. So this is the EPSG code also that can be used. So this thing I can copy it and put it inside. This also will take. Yeah, that is quite verbose, means many thing is there. Directly you can provide EPSG code and you can run it. Okay, now auto variogram I have told you. Then auto Krieg for automatic Krieging, means automatic this will do automatic Krieging and plotting, everything it will do. Just auto Krieg function you have to use. Within bracket you have to give the y variable tilde1 and the data in UTM or any projected system, and we are assigning it into Krieging result, and we can plot it. You can see this is Kriging prediction and Kriging standard error. As I have told you, this is a stochastic method. Kriging is a stochastic method, so it will provide error estimate also, standard error with semi-variogram. So all the things at a time it is giving. Now you see the shape is quite different. The output shape, we want this, we want it according to this outline, but if you see here, the shape is quite different. So if you want to have that shape, what you have to do, you have to convert the shape file into vector file, into raster file. So we are using rast function. This is coming from Terra package. Then we are using the extent of IRI, that shape file in UTM coordinate, and we want to generate the product in 10-meter resolution. So this resolution in 10-meter and coordinate system is in UTM. So this way you can generate a template raster. So this raster is having this many numbers of columns and this many number of rows, 295 columns and 288 rows with a resolution of 10-meter. And the coordinate reference system is UTM zone 43. You can have the extent also. So this, what we are doing now, we will be converting this raster, this template will be used to convert the shape file into raster file. That is called rasterization. From vector, we want to convert it into raster. The function is rasterize. Then you have to provide the shape file and a raster template. So by this way, we have generated a raster data. You see, now it has converted into spatial raster, spat raster. Otherwise, this boundary file was in vector format, spat vector, but polygon. You can see this was a polygon. So from polygon, we have converted into raster. So now we can plot it. This, you can see the resolution is very small, 10-meter. That's why the boundaries are very high resolution. The boundaries are appearing smooth. Suppose you put the resolution as 100. You can see the peaks. Then you will be able to visualize the pixels. You can see this has become pixelated. But we want the product to have 10-meter resolutions. So we have created this boundary. We can write this boundary raster also. And data type, we have written int for s. S is signed integer. Uh, this int is integer, and this is, I think, 4-bit system. So this way we can write it, and this boundary raster will be used as a, means whatever autocritic values are coming will be put one by one into these pixels, 10 by 10 meter pixels. So this autocritic, then SM till 1 input data, we have to give our UTM data. Then the new data, we have to give the boundary, but this boundary raster is in Tera format, spat raster. So we have to convert it into stars format, st as stars. This is the function. This star is another package like Tera. The stars package can handle your raster data, and SF package handles the vector data. Okay. So there are two workflows. One is Tera, and another workflow is SF and stars. So you can run it. It's running ordinary kriging for you. So it will take some time as we have generated the product at 10-meter resolution. That is quite high resolution. Now it has done. Now you can have the plot. Now you see those according to our boundary file, the maps were generated. And we can see how the soil moisture value is varying. It is varying between around something around 10 to 24%, and how errors are varying. And if you see where the observations are not there, these areas we were having less observations or no observations. The error were more in those areas. And where we were having more observations, the errors were less. We can have the structure, it will say what are the things inside that. And we can have a plot, this kind of thing, plotting with color output. So KR means if we directly plot it, suppose this, so it will generate a black and white plot, you see, grayscale, in grayscale. That is not appealing. So we want to plot it with 11 number of breaks. This break value we are assigning 11 number of breaks using a quantile break. If you are using ArcGIS or QGIS, when you are going to symbology, there you will find quantile, natural jinx, those kind of classification systems. So we are using quantile, and we are using this color ramp, MATLAB like 2, and we are this number within how many colors we want. So this has to be one less than number of breaks. So number of breaks is 11, it is 10, it should be 10. So now you can have this, you can see now it has converted into some colorful images. So you can see these areas are drier and these areas are having high moisture. Again, this area is having dry moisture content. So we can write it using the start package. So write underscore start kr, then kriging output. First output we want to write. This is sm underscore kriging tip. Directly you can write it. And if you want to write the error also, error can also be written. So second part, I think that is the error, standard error. So that part also is same kriging se. You can write it. Okay. This way you can write and you can have all those things in your drive. Okay. Now if you are having QGIS, you can directly open the QGIS. These things we have written in order to make a better visualization. So better plot, publication ready plot, you can use QGIS. Also you can use TMap, thematic map, or ggplot2 package available in R. So almost I am finishing. My part is finished. Just I will show you how to plot if the QGIS opens. And with that, this part of R spatial analysis, R for spatial analysis, is over. There are many things you can read from the internet. You can this just write Tera, TERRA, Tera R package. So they have this one. Some website is there. So Details are there in detail, like book format. You can read about this. So whether it is it is opening. So you can read each and every detail. So many things are available in the internet. If you are just typing Terra or stars or SF, so the packaging this all the functions, detail of the functions, how to use it with examples you can get from the internet. So mainly we have used RS Toolbox, Terra, SF, and Stars. These four package we have used for, and this four package will do most of the remote sensing data analysis for you. Okay, so I think it has opened. So just you can go layer, add raster layer. So three dots you can click and you go to your directory where you have the images. Suppose these two I want to open, edit. So those will be added here. And I think some classes are there on this and properties. This one, you can just close it, and this one can have properties and single band pseudo color. So here you can have equal interval of quantile, classify it into 5 classes. Why it is not continuous? Some problem. I don't know what is the problem, but no, some problem is there. That class is there. They will be showing you. I'm facing some problem. Okay, so that's all I wanted to share with you from my side.
Bappa, it was a very nice presentation and really for me like science extension. So it's a kind of eye-opening for me. But the one with two, three things I want to take from you, that is how to get shape files. Means that you have shown that you're taking the IRI boundary.
Okay, okay.
So that thing
Yes,
first.
fine.
Second thing, how to download the satellite data. And
Okay, these two questions.
yeah.
So these there is a separate dedicated class for that. That is there. You can have Earth Explorer in Google. You can type USGS Earth Explorer. So that will provide you Landsat 8, Landsat 9 data, and Copernicus. I have Copernicus. That is for Sentinel 1 and Sentinel 2. So those data, and also Google Earth Engine. You can write Google Earth Engine code to download Landsat 8 data. So ready-made codes are available. You have to write some code to download the data, because Google Earth Engine means level 2 product directly you can download. That is the beauty, and it will crop and mask everything in the cloud. No need to have a better computing system on our end. So it will be done in cloud. That is the beauty of Google Earth Engine. And save file for IRI, what we have done, we have used Google Earth Pro software. That is freely available software. Again, you can download that, install it, and suppose you type there New Delhi, you can zoom it in New Delhi area, and you can go, IRI, so you can go to your area, to your study area, and the boundary also. So there you can draw a polygon. So we have drawn a polygon and we have saved that polygon as shapefile or KML file. Directly, the KML file can be loaded into ArcGIS or QGIS or R. And also save files are available. That class is there. You can download the save files from internet. Some save files. But if you want to develop for your own area, you have to use Google Earth, the Pro.